MIT researchers have invented a cryptographic ID tag that is small enough to fit on virtually any product and verify its authenticity. It will be very useful to combat supply chain counterfeiting, which can cost companies billions of dollars annually. A 2018 report from the Organization for Economic Cooperation and Development estimates about $2 trillion worth of counterfeit goods will be sold worldwide in 2020. That is bad news for consumers and companies that order parts from different sources worldwide to build products. Counterfeiters tend to use complex routes that include many checkpoints, making it challenging to verifying their origins and authenticity. Consequently, companies can end up with imitation parts. Wireless ID tags are becoming increasingly popular for authenticating assets as they change hands at each checkpoint. But these tags come with various size, cost, energy, and security trade-offs that limit their potential. Popular radio frequency identification (RFID) tags, for instance, are too large to fit on tiny objects such as medical and industrial components, automotive parts, or silicon chips. RFID tags also contain no tough security measures. Some tags are built with encryption schemes to protect against cloning and ward off hackers, but they are large and power hungry. Shrinking the tags means giving up both the antenna package and the ability to run strong encryption. In a paper presented at the IEEE International Solid State Circuits Conference, the researchers describe an ID chip that navigates all those trade-offs. It is millimeter-sized and runs on relatively low levels of power supplied by photovoltaic diodes. It also transmits data at far ranges using a power-free backscatter technique that operates at a frequency hundreds of times higher than RFIDs. Algorithm optimization techniques also enable the chip to run a popular cryptography scheme that guarantees secure communications using extremely low energy. One innovation is an array of small antennas that transmit data back and forth via backscattering between the tag and reader. Backscatter, commonly used in RFID technologies, happens when a tag reflects an input signal back to a reader with slight modulations that correspond to data transmitted. In the researchers' system, the antennas use some signal splitting and mixing techniques to backscatter signals in the terahertz range. Those signals first connect with reader and then send data for encryption. Implemented into the antenna array is a beam steering function where the antennas focus signals toward a reader, making them more efficient, increasing signal strength and range, and reducing interference. This is the first demonstration of beam steering by a backscattering tag. Tiny holes in the antennas allow light from the reader to pass through to photodiodes underneath that convert the light into about 1 volt of electricity. That powers up the chip's processor, which runs the chip's elliptic curve cryptography (ECC) scheme. ECC uses a combination of private keys and public keys to keep communications private. In the researcher's system, the tag uses a private key and a reader's public key to identify itself only to valid readers. That means any eavesdropper who doesn't possess the reader's private key should not be able to identify which tag is part of the protocol by monitoring just the wireless link. Optimizing the cryptographic code and hardware lets the scheme run on an energy efficient and small processor. Currently, the signal range sits around 5 centimeters, which is considered a far field range and allows for convenient use of a portable tag scanner. Next, the researchers hope to push the limits of the range even further. The researchers also hope to fully power the chip through the terahertz signals themselves, eliminating any need for photodiodes. The chips are so small, easy to make, and inexpensive that they can also be embedded into larger silicon computer chips, which are especially popular targets for counterfeiting.